Today we're going to work through an example problem using the limit definition to find a derivative. This can all be found in section 2.5 of your lecture guide, so let's get started. We'll start with just a brief overview of what this example involves. Essentially, the rate of change or derivative of a function f at an input x is the limit of secant slopes between x, f of x, and nearby points x plus h, f of x plus h, and is given by f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. So I know that this sounds really complicated, but essentially this is just called the limit definition of the derivative. I think it's helpful to remember this whole process as having 8 steps and keeping track of them as you go to log your progress. So throughout this whole example, we're going to be using just the simple function 2x squared minus 1. The first step is to write the general limit definition of the derivative. This is just the formula mentioned in the last slide that we labeled the limit definition of the derivative. It states that the derivative of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. This is the formula you'll be plugging numbers into in the next few steps, which we're getting from the original function 2x squared minus 1. Restating the general limit definition of the derivative is just a good organizer of information and a reminder of the form that we're using. Step 2 is to rewrite the limit definition using the given function. This step will require finding f of x plus h. So we're essentially substituting the variables of our definition function into our given function. So if our definition function is f of x plus h minus f of x all over h, we start by looking at this f of x plus h expression. We take the x plus h variable and substitute it into our given function in place of x. This gives us the expression 2 times x plus h squared minus 1 in brackets. From our definition function, we then subtract f of x, which is just our given function in its natural form, hence our second pair of brackets, which we see above as subtracting 2x squared minus 1. So an easy way for me to remember it is essentially you're subtracting your given function from itself twice, but you're substituting different variables into it in both of those times from your definition function. So in your first expression, you've got that x plus h substituting in for your x in your 2x squared minus 1 function. And then you're subtracting just your original f of x, which is just your 2x squared minus 1. All of this always remains over h, so it's sometimes easy to forget to include the h as a denominator, so be sure to just focus a little bit extra on including this important variable. Another note is that after you write out the first step, you don't have to keep writing f prime of x, you can just write an equal sign with the limit and the function. Step 3 is to simplify the algebraic expression, showing one step at a time. We start by expanding x plus h squared. This is shown in red. Squaring x plus h means x plus h times x plus h, which gives us x squared plus 2xh plus h squared. Step 4 is to simplify the algebraic expression, now using distribution. Here we multiply the 2 by every value inside the parentheses and then the minus sign to everything in the parentheses. So this gives us 2x squared plus 4xh plus 2h squared minus 1 minus 2x squared plus 1. Step 5 is to simplify the algebraic expression by combining like terms. In red, I've shown you the terms that cancel each other out, leaving us with 4xh plus 2h squared. And this is because you have 2x squared minus 2x squared cancel each other out. And then you have minus 1 plus 1 cancel each other out, both equaling 0. Step 6 is to simplify the algebraic expression by factoring out and canceling a common factor of h. In this case, we have an h in our 4xh expression and an h in our 2h squared expression. We can then pull one h out from each of those to give us h times 4x plus 2h. We can then divide the denominator h into h to cancel the 2 out because h divided by h just equals 1. Step 7 is to show the limit of a completely simplified algebraic expression. This is just 4x plus 2h because, like I talked about in the earlier slide, you've divided h into h, canceling those two values out. And then finally, step 8 is to evaluate the limit as h approaches 0. This just means that we're plugging 0 in where we have any h in our expression. We conclude with writing our final answer as thus f prime of x equals 4x. And this is because you've substituted 0 into the 2h expression. 2 times 0 is 0, leaving us with just 4x. And these are just the 8 steps of finding a derivative using the limit definition. Today, we discussed an example of using the limit definition to find a derivative value. If you'd like some more individualized help, make an appointment with the tutor through the Academic Success Center, and they can give you some more tailored support.